Hi, everybody. Welcome to Physics C Mechanics. My name is Angela Jensvold, and today we're going to review torque. Okay. Why don't you guys give this one a try? Okay, so this system is balanced. So what we know is that the sum of the torques are equal to 0 on the system when it's balanced. And torque is RF sine theta. Okay, so if this is your axis of rotation where the fulcrum contacts the beam, you've got two torques acting. So you have this force here. Okay, this R is the distance is the vector that goes from the fulcrum to the point of application of the force. So technically it should be here, like that would be R. And then the force is straight down. Okay, that's the force of the Earth on whatever the object is here. I don't know what to call it, the object here. But r sine theta, because this is theta, theta is the angle between R and F. So since this is theta, this perpendicular distance here is actually r sine theta. Okay, so really you could say torque is the perpendicular component of the r vector multiplied by the force. So that's kind of a shortcut that really saves a lot of time, because how are we going to figure out what angle that is? We don't have the thickness of the beam, so we're just going to do r perpendicular. So let's do that. Okay, so we know the sum of torques are 0. So in the first case, they have 75 kilograms of known mass, and it's a distance x away. So this is 75 kg in the first case. So what that means, when the torque is equal to 0, that means that whatever clockwise torques has to equal the counterclockwise torques. And just like in math, you know how in math you have an angle like this, and that's positive, okay? Same in physics. So counterclockwise is positive, and just like in math, an angle that's clockwise would be negative. So our clockwise is negative and our counterclockwise is positive. So it's consistent with what you guys do in math class. Okay, so we're going to say, let's start with the positive torques, the counterclockwise torques. So that would be mass of the known g times 3, right? They gave us the distance is 3. That's r perpendicular. And that's equal to the clockwise torque, which is the mass of the unknown, g times x. Okay, if you cancel the g's, then you get mass unknown times x equals 3 times mass of the known. 3 times 75, that's 225, right? So we know mass of unknown x is 225. Now in the second situation, okay, the second trial, they used 85 as the unknown mass, and their unknown mass location is x plus 1. So let's set the clockwise and counterclockwise torques equal again. So in that case, you would have sum of torques is 0, still applies, right? So we have mass, the counterclockwise torque is mass unknown, g times 3, and that's equal to the, oh, that should have been known, right? That was the known mass, excuse me. So that was known mass G times 3. And the other one is mass unknown G times X plus 1, right? Okay, so if we plug in the known mass, which is 85, oh, can we cancel the G's first? 85 times 3, I think that's 255. I hope I'm right about that. 255. And on the right, you get mass unknown X plus mass unknown. Oh, but mass unknown X is 225 from the first data point. So let's do 255 equals 225 plus mass unknown. So mass unknown is 30 kilograms. Okay? So this is called equilibrium. Equilibrium is when the object is not rotating. There's no angular acceleration. Okay, so today we're gonna, before we dive in, I just wanna point your attention to one thing. If you go to AP Central, or sorry, if you go to My AP, AP Classroom basically, you can find some 3 free response questions that are similar in nature to what you're gonna see on this year's exam, you know, where you have to type in and submit. So it'd be nice if you guys could practice those. So this is how you get there. You log in at myap.collegeboard.org, and then, oh, sorry, this slide got a little bit messed up, but I'll write on here. So underneath this green box, it says AP Classroom. That's where you want to click. I have a feeling, hopefully you know that if you've been using AP Classroom this year, you just scroll down to your classes, and when it says AP Physics, C Mechanics, you go to the right and you click on AP Classroom. Then you go to here if you want to watch live videos. I have a feeling you know how to do that because you're here now. But if you want to do the optional student practice, let me change to red. Optional student practice, it's the first tab on the left. And then these all got shifted. So anyway, click here or here. You guys are going to have 3. So when you go to AP Physics C Mechanics, there are 3 optional free response practice. So you can click there to access them. And then you enter your response into that text box, right? This year, you're going to be able to type with a regular keyboard all of your answers. So you're going to upload your response. And then you're going to click submit. And it says, are you sure you want to submit? So click yes. But then here's the good part. It's going to say, before you submit, do you want to look at the rubric? You want to click yes. Then compare your answer to the rubric so you know where the points are allocated. So once you click on yes, I want to review, then it's going to show you this. So scroll down to see the rubric for each point, and you'll want to click part A, part B, part C, part D separately. Compare your answers. And then now you could submit. So you could click on no, submit now. Okay, so I hope you guys will go there and just practice typing in answers to physics problems. It's a good thing to do. So we're going to go over 5 learning objectives today. Here are the main ideas. This is the definition of torque. Okay, so it's a vector. You're taking a cross product of 2 vectors. And remember, R starts at the axis of rotation and it goes to the point of application of the force. These are the conditions for rotational equilibrium. This is how you find the rotational inertia of a system of point masses. This is if you have a continuous distribution of mass. You would have to integrate. And then this is the parallel axis theorem. That's if you have an object that's not rotating about its center mass. So torque is a vector product. This is where people get tripped up when they try to derive rotational inertia, is the dm. So lambda is linear mass density. So it's mass over length, or if you're looking at a differential, it'd be dm over dx. So usually the first step in deriving rotational inertia is to rewrite dm as lambda dx, and then you can integrate over distance, right? But then, of course, sometimes we have a two-dimensional, that's for a one-dimensional object. If you have a two-dimensional object, you would use mass per unit area. And then I'm sure you remember from from chemistry, rho, which is mass over volume. Okay, so these are the different types of densities we use. Parallel axis theorem, like I said, it's for when you have an object that's not spinning about its center mass. Oh, can you guys try this one? Okay, so basically you have a 40 kilogram student who's just balancing this board at L over 3, and they say, where would you want to put a 60 kilogram student to balance the board? Okay, well, if you think about it, okay, we know that some of the torques are 0. So the clockwise torque is from the earth pulling down on the board, and then the counterclockwise torque is from the student, right? So in the first instance, the 40 kilogram student, their torque is exactly matching the torque from the earth pulling on the board. And in the second instance, you also want the torque from the student to exactly match the torque from the earth pulling on the board. So basically, you want the torque from the 40 kilogram student to equal the torque from the 60 kilogram student. Okay, so what do we have here? Again, with the same thing, I know that R would be kind of like, whoa, that wasn't a very good line, was it? R would kind of be like this. That's R, and then F is like this. So, but what we care about is the R sine theta, this one here, R sine theta. Okay, and that is L over 3. So we're going to do, 40 is what I wanted to do. 40 G L over 3. That's the torque from the 40 kilogram student. And we want that to equal, let me just remind you, torque is RF sine theta. R sine theta is L over 3, and F is mg. Okay, and then we want that to equal the torque from the other student. So that would be 60g, and we don't know, let's call it x. We don't know how far that person is from the pivot point, so we're going to leave it blank. Let's cancel our g's though. So we get x equals 40L over 3 times 60. So that's 2L over 9. Okay. Okay, try this one. You got to find little m. Okay, so these systems are in equilibrium. So we know the main idea is that the sum of their torques are going to be 0. Okay, so that means that the clockwise torques and the counterclockwise torques should be equal. And here's our fulcrum. Okay, so on the left, and the situation on the left, the positive torques would be mg_L1, and that has to equal the clockwise torques would be m1g_L2. Cancel the g's. And solve for L1 over L2, and you would get M1 over little m. Okay, now let's look at the right-hand situation. Same thing, basically, you have the system's in equilibrium, so the counterclockwise and the clockwise torques have to balance. So you would do M2 L1 equals M L2. So little m would be M2 L1 over L2. But L1 over L2 is M1 over M, right? If you solve for M, you get square root of M1, M2. Okay, this is more about experimental uncertainty. Try it. Okay, the question is, in this situation, why would the measured tension be greater than the theoretical tension? Okay, the radius of the hinge is not negligible. I'm going to skip that one. I don't really know what that means. The linear density of the short cable increases vertically. I don't think the linear density of the cable is, I can't think of a reason that would affect. The linear density of the bar decreases. So that means there would be more mass closer to the hinge. If there were more mass closer to the hinge, then it wouldn't take as much torque to prevent it from rotating. So we would measure less tension, not more. The rotational inertia of the bar about the hinge is less than, well, C and D are almost the same thing. So if there's less rotational inertia, it doesn't need as much torque to prevent it from rotating, right? So you would measure less tension, but here we're measuring more. The rotational inertia is greater than 1/3 ml squared. If the rotational inertia is greater, that means you need more torque to prevent it from spinning. Okay, try this one. Okay, so the system is in equilibrium, rotational equilibrium. So you know the sum of the torque is equal to 0. Here is your pivot point at the hinge. So what we want to do is say this is a counterclockwise torque, right, from the tension in the cable. So that'd be positive. So it would be tension times the length of the beam times the sine of theta. And then this torque would be clockwise. So the torque from the earth pulling down on the beam is clockwise, so it's negative L over 2. The force acts at the midpoint of the beam times the weight equals 0. That one's at 90 degrees, so sine of 90 is 0. Sorry, sine of 90 is 1. So let's cancel those L's and get them out of the way. And then we solve for tension, which would be W over 2 sine theta. Okay, try this one. Okay, so we need the definition of torque, which is RF sine theta. So here's your pivot point all the way to the left of the arm where the shoulder is, right? And then you want from the weight of the hand. So the weight of the hand acts here. So that would be the mass of the hand times G, right? So R is this distance here, that vector. So it would be 0.6. Sorry about that. 0.6 meters. And then the force would be the mass of the hand times G. So it would be 10 newtons. And then you have the sine of what is the angle between R and F? 90. So it's 6 Newton meters. Okay, here's a free response for you. Okay, so first we have to find the tension in the string, and you know this system is in equilibrium, so we know that the sum of the torques are equal to 0. So what we want to do is take the clockwise torques and set them equal to the counterclockwise torque. Well, there's actually two counterclockwise torques. Okay, anyway, let's add those torques together. So it would be from the block, it would be 2 mg, that's the force of the earth pulling down, times how far it is from the axis, which is 2r, multiplied by the sine of the angle, here's r. R goes from the axis of rotation to the point of application of the force. And the sine you know, alternate interior angles, right? So if this is theta naught, this is also theta naught. Sine theta naught plus the torque due to the rod itself, the earth pulling down on the rod itself, which has a mass m, so it would be mg, and it's the earth is pulling at the center of the rod, which is a distance r from the rotational axis. And same idea here, alternate interior angle, so it'd be sine theta. And that's equal to the clockwise torque from the tension of the string, which is just T times R, 90 degrees there. So we don't have to worry about the angle. Could we maybe cancel the R's? Okay, and then, so we're trying to find tension. So tension would be 5 mgr sine theta naught. Okay, and then in part B, it says, now they cut the string, find alpha. Okay, well, alpha is sum of torques over I. So that is the rotational analog for Newton's second law. So this is Newton's second law for rotation. Usually it's A is sum of forces over mass. Now it's alpha is sum of torques over rotational inertia. So what are the torques? If you cut the string, what torques do you have? Just the torques from the rod and the block, right? So if we go back up here, I guess I will circle it in black. This is equivalent to the torque from the rod and the block. So I'll just add those together. It would be 5 mgr sine theta naught, right? And then the rotational inertia, they gave us the rotational inertia of the disk, 3/2 mr squared. They gave us the rotational inertia of the rod, 4/3 mr squared. And then you have to do the rotational inertia of the block. You can treat the block as a point mass. So its rotational inertia would be mr squared, and its mass is 2m. And how far is it from the rotational axis? 2r. Okay, so what can we do? We could cancel, let's cancel some masses. Cancel all these m's. Can we cancel one of these r's without getting in trouble? Just going to cancel the squares. I don't really know what to do here. I'll just put an arrow there to remind myself. Okay, now I got to simplify. So alpha is 5g sine theta naught on top divided by, I think it would be, the common denominator is going to be 6, right? So this will be 2 times 3, so 9/6 plus 8/6 plus 2 times 2 is 4 times 8, 48/6. And then it's just r on the bottom, right? Because we canceled one of the r's. All right. So it's 5g sine theta naught over, what is all that? 48, 57, 57 plus 8, 65 over 6r. And then I guess I'm going to cancel this 5, and this would be a 13. So it'd be 6g sine theta naught over 13r. I don't know why I keep writing theta 2. All right, so that's alpha. And then we want the linear acceleration of the block, okay? So linear acceleration is alpha r, right? But how that r is how far the block is from the rotational axis. It's 2r away from the rotational axis. So you have to take the alpha we just found, 6g sine theta naught over 13r, and multiply by how far the block is from the rotational axis. So once you do that, you'll get 12g sine theta naught over 13. And then it says, find the linear speed of the mass at the end of the rod in the diagram shown. So basically it went from that angle theta naught all the way to horizontal, and we need to find the tangential speed of the block right when it gets horizontal. So let's use energy conservation. That's usually the easiest. Okay, so we'll do E initial equals E final. And the system has gravitational potential energy. I'm talking about the rod, disk, block, earth system. So it would be, let's see, 2 mg. Now, how far did the block fall from this angle to horizontal? Do a little geometry. It was like this, right? So r, and then this angle is theta from the vertical. So that means this is theta. So that the vertical distance it fell was r cosine theta. Okay, so 2 mg, did I mess up the r? Isn't it 2r? Should be 2r. If my students were here, they would help me. Okay, plus, and then the rod itself has a mass of just m. So mg times how far it fell. So that one only fell r cosine theta naught. Okay, so that is the change in gravitational potential energy of the system as it went from here to here. Where did that energy go? It was transferred into kinetic energy, right? So that would be 1/2. Now it's not 1/2 mv squared. This thing is rotating, so we're going to use rotational kinetic energy. And the total rotational inertia is in the denominator up here. What should I do? I'll box it in yellow. This denominator is the total rotational inertia of the system. So I don't feel like deriving it again. So I'm just gonna look up there and do a little simplifying. 3/2, oh, that ended up being 65 over 6, right? I don't wanna do that again. 65 over 6 mr squared, okay? Times omega squared, but omega is v over r, okay? So omega is v over r. But the thing is, we're talking about the linear speed of the end of the rod, and the end of the rod is a distance of 2r from the axis of rotation. So this should be v squared over 2r squared. So this is omega squared, right? So I substituted in v over r for omega. And now I think we can cancel something. Let's cancel the m's first. Let's cancel these r's here. Okay, now I think we just gotta do a bunch of algebra. Okay, so this would be 5 gr cosine theta naught over whatever's in front of this v squared. There's a 4 on the bottom, so that's 24, 48. This would be 65 over 48. Is that it? Yeah, I guess that's it. Okay, so then we flip it up. Actually, I want to cancel the 5 first. 5, and this will become 13. So it'll be, I almost forgot to square root. Wow, so much algebra. Okay, so it's the square root of 48 gr cosine theta naught over 13. And that 48, it's 16 times 3, right? So you can take a 4 out, square root of 3 gr cosine theta naught over 13. Okay, so that was crazy, but we did it. Okay. So I'm gonna clear this and just say what we used. We used, obviously, sum of torques is 0. We know V is omega R. We used alpha is sum of the torques over rotational inertia. Oh, rotational kinetic energy is 1/2 I omega squared. These are all rotational analogs for the linear quantities. And I think that's basically all we used in this problem. Okay, try this one. Okay, so originally, they're telling you that there's 2 ropes on the ends, and the left rope has a tension of 150. Okay, I kind of feel like, okay, if you call the center the axis of rotation, you know that the distance from here to here is L over 2, and the distance from here to here is L over 2. So if you know there's the same distance from the axis of rotation and it's in equilibrium, they have to have the same tension. So this would also be 150 newtons. Now, what can we do with that? Well, we know that the sum of the forces in the y direction are equal to 0, right? Because it's in translational equilibrium and it's also in rotational equilibrium. So I know that the sum of the torques are 0, but the sum of the forces in the y are also 0. What can we do with that? We can say tension from the left-hand string plus tension from the right-hand string minus mg is equal to 0. So if we solve for the weight of this beam, it'd be 300 newtons, right? Okay, so we've got that. Now what they're going to do is they're going to move this right string. They're going to move it to point R. So we don't know what this tension is going to be. That's what we're going to try to find. Okay, so now we're going to sum the torques and set it equal to 0. So what I want to do now with the red situation is I want to call this my axis of rotation because it's going to make my life easier. There's many ways to do physics problems, and it's not wrong, but I just know it's going to be easier putting my axis of rotation on the left. And part of this, my students always ask me, how do you know where to put the axis of rotation? It's usually comes from experience. So I think if you guys practice, you'll become better and better at seeing from when you start the problem which direction you should go. So, but trial and error, experience. So if the left contact point is the axis of rotation, then there's a torque from the weight of the beam, right? That's clockwise. And then there's a counterclockwise torque from the rope pulling up. So the positive torques would be tension from the rope, 3L over 4, 3L over 4, minus the weight of the beam times L over 2. All of that has to add up to 0 because the system is in equilibrium. Okay, so let's cancel the L's, get them out of here, and you're solving for tension in the rope. Tension in the rope is the weight of the beam, 300 over 2, so that's 150, divided by 3 force. So what is that? 50 times 4 is 200. 200 newtons, which means that the left beam must be pulling up with 100 newtons because those 2 ropes have to support the weight of the beam. And if the beam is 300 newtons and the right string pulls up with 200 newtons, the left string must pull up with 100 newtons. Okay, try this one. Okay, so first we're going to draw a force diagram. So we've got tension of the string on the rod. We have the force of the earth on the block, and we have the force of the earth on the rod. These are not drawn to scale. And then there's the force of the hinge on the rod. So those are the four forces acting on the rod. And then you want to find the tension in the string. Okay, they're asking for the reading on the spring scale, but that's the same as the tension in the string. So we know this thing is in equilibrium. So we're going to set the torques equal to 0. So the positive counterclockwise torques have to equal the negative clockwise torque. So let's start with, there's only one counterclockwise torque. So that's tension of the string on the rod times the length of the rod times the sine of 30 minus the mass of the block G times L minus the mass of the rod G times L over 2, because the force of the earth is acting at the center of the rod, so that's only L over 2 from the axis of rotation. The axis of rotation is here at the hinge. Let's cancel those L's. The L's go away, and you get tension is mass of the block G, that's 5, plus mass of the rod G over 2, that'd be 20 divided by 2 is 10, all over sine 30. So it's multiplied by 2. So it's 30 newtons. The tension in the string is 30 newtons. Okay, and then it says the rotational inertia of the rod about the center is 1/12. Find the rotational inertia of the rod block system. Okay, so now we need to use the parallel axis theorem. So we're going to do the rotational inertia about the center of mass plus mh squared. And h is the distance from the axis of rotation to the center of mass. Okay, so we're going to do the 1/12 that we were given plus the mass of the rod. And how far is the center of mass from the axis of rotation? L over 2. Okay, so that ends up being 1/4 plus 1/12 is 1/3 ml squared, but we're not done. We're not done because they were asking us of the rotational inertia of the rod block system. And the block is a point mass, so we're going to say I total is I rod plus I block. Okay, so I rod is 1/3 ml squared plus the block would be a point mass, so that'd be m, and it is L away from the center, from the axis of rotation. So when you add those up, you should get 4/3 ml squared. Oh, you know what? Wait. Oh, I'm being so careless. Did you guys notice how careless I'm being? This is the mass of the block. This is the mass of the rod. I almost went down a dark path. Okay, mass of the rod is 2, so 2/3 times 0.36. I squared 0.6 to get 0.36, plus mass of the block, which is 0.5 times 0.36. I squared the length of the rod, 0.36. I squared 0.6 to get 0.36. Okay, anyway, all of this adds up to 0.42 kilogram meter squared. This makes me think, because my friend sent me, her students did a promposal, and they had to do promposal even though there's no prom. But one of them I really liked the best. It said, I'm not very good at deriving rotational inertia, but even I could see us spinning at prom. Like because rotational inertia. I thought that was very clever. Okay, D, if the chord that, okay, you're going to cut the string, calculate the initial alpha. Okay, so we did this before. This is sum of the torques over I. So what are the torques acting on this system? Well, let me go back up to the beginning. I'm not going to redo this because I'm just going to use this. Did it already. I'm not doing it again. So the tension of the string, it's gone. They cut it. So we're only left with those two torques. So it would be minus mass of the beam, so 20 times the length of it, 0.6, minus That's block, not beam. Oh boy. It's okay. 5. Okay, and then now we have the mass of the rod. So it's 20 times 1/2 all over the rotational inertia, which we just calculated, 0.42. And you should get for alpha negative 21.4 radians per second squared. Okay, that's kind of fun. Oh my gosh, we're out of time. All right, why don't you guys do this for homework, okay? Find F2 if the wheel moves at constant angular speed, okay? Do that for homework. Tomorrow, we'll go over it. We're going to do rotational kinematics, which is a piece of cake. You're going to love it, okay? Everybody stay home. I'll see you soon.